The next two theorems have to do with properties on the return function that get carried over to a monotonicity and a concavity property on the value function. Okay, but again, so when I say the value function, it's the value function of the original problem, the sequences problem. But under bounded returns, we've seen that the Bellman equation, the functional equation, has a unique solution V. So along with the earlier results that say that the value function is one of the solutions of Bellman's equation, we're going to use this unique solution to the functional equation as the value function, okay, when we go around proving these. Right? So on the monotonicity, we make two assumptions, one on the return function and then a corresponding assumption on the feasibility correspondence. Assumption 5 is that the return function is strictly increasing in the current state x. Okay, so the current state x in the return function is just, if the state is a variable, then it's just the first argument, which is some real number. If the state is a vector living in RL with L components, then x itself is a vector, and so by saying f is strictly increasing in x, we mean that it's strictly increasing in the L arguments of x. Okay? For instance, in the optimal growth model, f of xy is given by this function here, per period utility of consumption, which here is f of x minus y. So again, interpret x to be the current state in the optimal growth model, which is the current capital stock, and y is next period's capital stock. Okay, so f of x minus y is consumption. So here, if x increases, so will the full output f of x, right? And holding y constant, f of x minus y, the consumption increases, and so will u, right? So u is increasing in x. Assumption 6 says that the feasibility correspondence gamma is monotone. So in what sense? In the sense that if x prime is greater than or equal to x, then the feasibility choices gamma of x prime, those form a superset of the feasibility choices gamma of x. Yeah. So before illustrating this, let me again flag that this x can be a real number or a vector in RL. Okay, so this inequality x prime is greater than or equal to x can be an inequality of real numbers, or it can be a vector inequality. Okay, so illustration. In the optimal growth model, gamma of x is the closed interval from 0 to the full output f of x. So now if x prime is greater than or equal to x, the full output f of x prime is greater than or equal to f of x. And so the closed interval 0 to f of x prime is going to contain the closed interval from 0 to f of x. Okay. Theorem 7. Let these parameters, state space, feasibility correspondence, return function, and discount factor, satisfy assumptions 3 to 6. So 3 and 4 as before, right? So let me quickly remind you what assumptions 3 and 4 are. So assumption 3 is an assumption on the state space being convex and the feasibility correspondence essentially satisfying the theorem of maximum assumptions, that it be non-empty valued, compact valued, and continuous. And assumption 4 is on the return function. It requires the return function to be bounded and continuous, and the discount factor to be strictly between 0 and 1, right? So along with these assumptions now, assume also that assumption 5 holds, that is, the return function is strictly increasing in current state x, that's in its first component of the return function, and that the feasibility correspondence is monotone, right? So suppose theorem 7 says, suppose these 4 assumptions are satisfied, right? Then the value function, or what is the same thing now for us, the unique solution to the Bellman's equation, V, is strictly increasing also. So if capital F is strictly increasing, so is V. Okay? And the thing to note about why this happens is because the non-decreasing functions form a closed subset of, so let me take that back. The bounded continuous and non-decreasing functions, C prime of x, are a closed subset of the bounded and continuous functions, C of x, okay? So we will so let's look at the argument of closedness first. So why the bounded, continuous, and non-decreasing functions constitutes a closed subset, right? So take a sequence Wn of functions that lie in C prime of x. So each function in Wn is bounded continuous as well as non-decreasing, right? So what does each function Wn satisfy? It satisfies that if x is less than or equal to x prime, then Wn of x is less than or equal to Wn of x prime, okay? Each function Wn satisfies this, right? So please remember that the x lies in a state space and in principle can be a vector, and that the Wn of x is a real number, okay? So now suppose the Wn's are non-decreasing functions in this way, and suppose the Wn functions converge to a function W, right? So in order to establish that the set of bounded, continuous, and non-decreasing functions is a closed subset, we show that this W, this function W, is also non-decreasing, okay? So I should say, suppose Wn converges to W in the soup norm, right? So if that happens, you should be able to show that Wn continuous implies that the limiting function W is continuous, right? The limiting function in terms of the soup norm. So we've established this in our metric spaces module. And similarly, Wn bounded, you should be able to show that W is bounded. It's a good exercise to do these, okay? So we look only at the third implication right now, which is Wn, all Wn non-decreasing implies W non-decreasing, right? So that is kind of obvious now. So Wn converges to W in the soup norm implies Wn of x converges to Wx for each x, right? Because the soups converge. So the soup of the difference between Wn of x and Wx goes to 0. So that means each of these must be going to 0, right? Right. So now Wn of x is less than or equal to Wn of x prime, and let n go to infinity. So then Wn of x goes to W of x, Wn of x prime goes to W of x prime, right? And we know that the weak inequality will get preserved in the limit, right? So we keep saying that the weak inequality will get preserved in the limit, and we've done a little bit of this now, but I'm expecting you to sort of be completely comfortable with the idea that a weak inequality will get preserved in the limit, but a strict inequality will not. A strict inequality may get converted to a weak inequality, right? So if you have any doubts about this, please think about it a little bit, and we can also discuss this, right? So W itself is also a non-decreasing function, and therefore this set of functions C prime of x is a closed set, okay? So now suppose I start with a function f that is closed, so that is bounded, continuous, and non-decreasing, right? Then the claim is that using the Bellman map, Tf, the function Tf, is going to be bounded, continuous, and strictly increasing, okay? So here when I say f, I'm going to use f as a sort of value-like function because I'm using the Bellman map, right? So suppose x is less than or equal to x prime, right? F is non-decreasing, so let me come back to this a little bit. So f is non-decreasing. What we want to establish is that Tf is strictly increasing. So we want to establish that Tf of x is strictly less than Tf of x prime, okay? So what is Tf of x? Tf of x is the right-hand side of Bellman, which is the max of f of xy plus beta small f of y, yeah, over all feasible y, right? So here, using the notation that let y bar be a maximizer. Remember that the maximizer set may not be unique, right? But it has certain properties given by the previous theorem. Let y bar be a maximizer of this right-hand side, right? So then this max will be equal to f of xy bar plus beta f of y bar, okay? So now use the fact that the capital F function has been assumed to be strictly increasing by assumption 5, okay? So strictly increasing, so for the capital F function, this is true. X less than x prime implies f of xy less than f of x prime y, yeah, for all y. Right? So this is going to be less than f of, so strictly increasing would be x less than x prime. We want to imply that tf of x is less than tf of x prime, okay? So this should be indeed let x be less than x prime, okay? So the first term, f of x prime y bar, is greater than f of x y bar. So f of x prime y bar plus beta f of y bar, yeah, or let me put it the other way, f of x y bar plus beta f of y bar is strictly less than f of x prime y bar plus beta f of y bar, okay? But now, when the current state is x prime, y bar may no longer be a maximizer, right? So we said let y bar be a maximizer when the current state is x. When the current state has increased to x prime, y bar may no longer be a maximizer, but y bar is available, right? So x is less than x prime, right? So that implies that gamma of x is a subset of gamma of x prime. We had pulled the y bar out of this set. So y bar also belongs to this set, but it may no longer be the actual maximizer. So whatever this value or this number is must be less than or equal to the maximum value that can be attained when the state is x prime. Okay, and this maximum value using the Bellman map is Tf of x prime. Okay, so this shows that if we start with a non-decreasing f, then one iteration with t is going to take us to a strictly increasing Tf, right? And that's because we are adding this strictly increasing capital F here, okay? So the strict inequality happens since f is strictly increasing in the first L arguments, right? But then we have that T is a uniform contraction on, so T is a uniform contraction, right? And so it has a unique fixed point, right? So unique fixed point V, right? Now, moreover, we have that the corollary of Banach's is satisfied in this way, that there is a closed subset C prime of X, a closed subset, and the closed subset has this strong property that T of C prime of X, right? So these are my bounded continuous non-decreasing functions, okay? But T of C prime of X let me just say equal to, I could, right, is some subset C double prime of X that is a subset of C prime of X. Okay, C double prime of X is the bounded continuous strictly increasing functions. Okay, so then using the corollary of Banach's theorem, it must be the case that the unique fixed point V lies in C double prime X. So the unique fixed point V is bounded, continuous, and strictly increasing. Okay? So next, as an alternative here to strictly increasing, although we can use everything together, but as an alternative, consider a function f that is strictly concave, right? So remember that the argument of f is x comma y. So f strictly concave would mean that for every pair of xy, x prime, y prime in the graph, and for all theta between 0 and 1, f of theta xy plus 1 minus theta x prime y prime is greater than or equal to theta f of xy plus 1 minus theta f of x prime y prime, and in fact is strictly greater, strict concavity, strictly greater if x is not equal to x prime. Yeah, we could go the whole hog and say strictly greater if xy is not equal to x prime y prime, and that would be fine. What we'll need is only this much. Corresponding to f concave, we assume that gamma is in some sense a convex feasibility correspondence. In what sense? In the following sense, that for every theta between 0 and 1 and x and x prime belonging to capital X, the state space, right? If y is a state that is feasible from gamma of x, that belongs to gamma of x, and y prime is feasible at x prime, right? The convex combination of these two feasible states, theta y plus 1 minus theta y prime, is feasible at theta x plus 1 minus theta x prime. Okay? So I'm wondering whether this will be satisfied by the, so will assumption 8 be satisfied in the optimal growth model? Yeah. So to rephrase in the notation of that model, I guess what we are saying is if next period state y is feasible at current state k and y prime is feasible at current state k prime, then for any theta between 0 and 1 is next period capital stock theta y plus 1 minus theta y prime. Is this feasible? Does it belong to? So now you have to be a little bit careful. So does it belong to gamma of theta k plus 1 minus theta k prime, right? So this was gamma of k, this was gamma of k prime, right? So does it belong to this? So it's saying, does it belong to the closed interval 0 to f of theta k plus 1 minus theta k prime? Yeah. Okay. So recall whether we had used whether we had assumed some implication about the full output function lowercase f being a concave function, yeah, starting with the actual production function being concave, and whether you can use that to show this, right? So you should be able to. So the next theorem is, suppose these parameters in the optimization problem satisfy assumptions 3, 4, and now 7, 8. Yeah, basically that the return function is strictly concave in its arguments, right? Then, so now this says v star instead of v, but please remember that what we are interested in is the value function v star of the sequences problem, because that's the problem that we want to solve, right? What we can use is the unique solution v, because they are the same. Okay, so suppose these assumptions are satisfied, then v star, the value function, is strictly concave, and the optimal policy correspondence, capital G, is now a function. It's a continuous single valued function. Yeah. So suppose C double prime, C prime, and C are the following. So these are the bounded continuous functions. These are the bounded continuous concave functions. These are the bounded continuous strictly concave functions. Then they're going to follow this nesting, right? So now what is being said is that the bounded continuous and concave functions, because they follow weak inequalities, not strict inequalities, they're going to constitute a closed subset of C of x, right? So again, the idea is, suppose Wn is a sequence of bounded continuous and concave functions, right? So remember, these are value-like functions. They're written on the state space X, right? So due to concavity, each Wn is going to satisfy these weak inequalities. For every pair x prime and theta between 0 and 1, Wn theta x plus 1 minus theta x prime is greater than or equal to theta Wn of x plus 1 minus theta Wn of x prime, right? And now you let n go to infinity, right? Then because the Wn's converge to W in the soup norm, right? So converging, I should say uniformly converging, or converging in the soup norm, right? So n goes to W. The left-hand side will go to W of theta x plus 1 minus theta x prime. The right-hand side will go to theta W of x plus 1 minus theta W of x prime, and the weak inequality will be preserved. So the limiting function W will also be concave. We've already shown that it will also be bounded and continuous, and therefore the set C prime of x of these concave functions is a closed subset, right? So we will be able to apply corollary 1 of Banach's theorem if we show that once we pick a concave function, let's say f, then the function Tf obtained through the Bellman map will be strictly concave. Yeah, that will show that T of the concave functions, yeah, they are a subset of the strictly concave functions, or they are equal to the strictly concave functions. Yeah. And since this is a subset of the concave functions, by the corollary of Banach's theorem, the unique fixed point must belong to this set, the strictly concave functions. Okay? So all we really need to show is that if f is a value-like function which is concave, then Tf is strictly concave. Okay? So suppose we take two current states, x prime, x double prime, and some theta between 0 and 1. And suppose we use this notation that y prime maximizes the right-hand side of Bellman when the current state is x prime, and y double prime maximizes it when the current state is x double prime. Okay? So in particular also, that means y prime must be feasible when the current state is x prime, y double prime is feasible when the current state is x double prime. And so theta y prime plus 1 minus theta y double prime is feasible when the current state is theta x prime plus 1 minus theta x double prime. Okay? So so the inequalities are getting cut here. Okay. Never mind. So what do we have to show here? We have to show that Tf is strictly concave, right? So we have to show that for all x prime, x double prime in x and theta in 0, 1, TF of theta x prime plus 1 minus theta x double prime is strictly greater than theta TF of x prime plus 1 minus theta TF of x double prime. Yeah, I should not say for all. We want to prove a strict inequality. So for all x prime, x double prime with x prime not equal to x double prime. Okay. So yeah, so because if there's inequality, then if there's equality between x prime and x double prime, then there'll be an equality here, right? So that's not the objective of strict concavity. Okay, so now TF of theta x prime plus 1 minus theta x double prime, by definition of Bellman, is equal to this right hand side. So let me complete this right hand side. So it's max over all y that are feasible at theta x prime plus 1 minus theta x double prime of f of the current state theta x prime plus 1 minus theta x double prime y plus beta f of y. So the only thing to complete here is a square bracket. Okay, so that is TF at the current state theta x prime plus 1 minus theta x double prime. Okay, now we had assumed notation which said let y prime be optimal and therefore feasible at x prime and y double prime be feasible at x double prime, and in fact be optimal there. Yeah, so in particular they're feasible and therefore theta y prime plus 1 minus theta y double prime, yeah, that's feasible at the state theta x prime plus 1 minus theta x double prime. Okay, so max, whatever the max is, must be greater than or equal to the return function capital F with this current state and this particular choice of y. Okay, a convex combination of y prime plus y double prime. Okay, this particular choice, so plus beta times the value like function f of this particular choice, theta y prime plus 1 minus theta y double prime. Yeah. Okay, so the max must be greater than or equal to this because we've now replaced an optimal y with this particular choice, and this particular choice need not be the maxima, need not be a maximizer when the state is theta x prime plus 1 minus theta x double prime. Okay, right. And then we use the strict concavity of capital F to say that the first term here, yeah, is strictly greater than theta f x prime y prime plus 1 minus theta f x double prime y double prime. Okay, and so there is a strict inequality here because f is strictly concave, right? And because the value like function lowercase f is weakly concave, there's a weak inequality here. So plus beta times theta f of y prime plus 1 minus theta f of y double prime. Okay, and now we just collect the terms separately. So this is a theta capital F x prime y prime plus b beta f y prime. So why are we doing this? We're doing this to get right hand side of Bellman here. All right. So theta f of x prime y prime plus beta f of y prime is theta t of x f of tf of x prime. Why is that? Because we had assumed that x prime is a maximizer when the current state is, sorry, y prime is a maximizer when the current state is x prime. Yeah. And then the next two terms, plus 1 minus theta f of x prime, x double prime, y double prime, plus beta f of y double prime, yeah? And that's equal to 1 minus theta tf of x double prime, because y double prime is a maximizer at x double prime, yeah? And so we've shown that tf is a strictly concave function. And now we can apply the corollary of Banach's theorem to say that the fixed point V, the unique fixed point V, lies in C double prime. Okay, it's strictly concave. Right. So recall that the unique fixed point satisfies for each current state x that V of x is equal to max okay, it satisfies this. So this is strictly concave, the unique fixed point is strictly concave, so this thing is strictly concave. And so there will be a unique maximizer. So for every x, there is a unique maximizer, right? And that means that the optimal policy correspondence is just a function, okay? So remember that this was the set of all y's such that f of xy plus beta v of y is the max value of Bellman, right? So now this is a singleton. And because it's a singleton, we may get rid of the correspondence machinery and just say that this is a function, the optimal policy function, okay? The next theorem, which we state without proof, says the following, that in this strictly concave environment where the return function is strictly concave and as a consequence the unique value function, so the value function, which is the unique solution to Bellman's equation, is strictly concave as well. The policies are unique at every state, so there's an optimal policy function. So then the theorem says, suppose you start with any value like function v naught, right, and you iterate your way, to the unique value function, right? And suppose we use the notation that the unique, or not the unique, so the optimal policy correspondence is G. Yeah. So optimal policy function is G at V, okay? Now at any Tn V, when that is your value like function, let the optimal policy function be Gn. So then the result says that as Tn V naught converges to V, Gn converges to G. Let's state this a little bit clearly, but without proof. So consider the iteration starting at any Vn, going to Tvn using the Bellman map. So Tvn of x is max over feasible y's of f of xy plus beta Vn of y, right? And call this Tvn, give this the name Vn plus 1. Okay, so then we are starting with a V naught, we are going from that to a V1, which is a TV naught. Then we are going to a V2, which is a TV1 or a T2V naught. Then we are going from that to a V3, right? So that's a T3V naught, and so on. Yeah, Vn plus 1, and so forth. So Tn V naught, Tn plus 1, V naught, right? So let V be the unique solution to the functional equation. So that by implication here is just that we'll converge to the V. Yeah. And let G be the optimal policy correspondence. That is, this is in some sense, it is the value function, and G is the corresponding optimal policy correspondence. Okay? So at each x, G of x is the argmax over the y. So it will pick out the unique y which maximizes current returns and future returns evaluated with the y, with the v, when the current state is x. So this is my optimal policy function G of x. Right? Now for each of these iterations n, let Gn be the maximizer policy function when I'm using the value like function Vn here. Okay, so let Gn of x be the argmax of f current returns f of xy plus beta times Vn of y. Okay, so the result says that then Gn converges to G. So why can this be useful for us? It can be useful when we use, let's say, a value or a policy iteration to obtain the unique value function. So typically what we do in a value iteration algorithm is we start with some arbitrary value like function V naught. We know what the Bellman map is, right? So we apply it a large number of times. So then we are sort of assured that we are somewhere very close to V, right? So we are very close to V, but we may still not have actually reached V, right? So what we are saying is that if n is large, we are in some very small neighborhood of the function V, right? And then what we typically do is we say, well, we will treat this V as the actual value function, and we will take whatever the policy function there is to be our G. okay? But if v is not the actual value function, but just some Tn v naught for n large, so it's very close to this, then what we are actually taking is a Gn, right? What we're taking for G is a Gn. Yeah. So what this theorem shows is that in a concave environment, this Gn will be very close to our optimal policy function G. Okay. So we can stop here because of domestic reasons right now, and then continue